hard to find these. If you did this in your analysis lab, these cells can be very difficult to find. It's not very common. Eosinophils are responsible for attacking parasites. So an eosinophil these are specifically involved in attacking eukaryotic parasites. So if we have a patient with an infection, a worm infection or a protist infection, these are not terribly common here in the developed world, but they do happen. If a patient is dealing with a eukaryotic organism that's causing infection, often we will see an elevated eosinophil count. And again, those guys stay in red. The basophils, their major role is to stimulate inflammation. And as a side effect of stimulating inflammation, they stimulate the allergic response. One of the things a basophil does, it secretes histamines. Histamines stimulate the allergic response. So if you are taking an antihistamine, what you're doing is you're trying to block the signaling by basophils. You're trying to block an inappropriate inflammatory response by being exposed to something like pollen in the atmosphere, where you're getting inflammation developing. You get those unpleasant symptoms of allergy. In some cases, though, that inflammation is actually necessary if we're fighting an actual real infection. Inflammation can help clear out microorganisms. So their real role in the body is not to give us allergies. Their real role is to stimulate inflammation when it's necessary, when we're dealing with some sort of infection. The whole allergy symptom, that's just kind of a byproduct of the activity of the basophils. So again, antihistamines can block this signaling and reduce our symptoms associated with inappropriate inflammation and allergy. So not a lot of detail here. This is not something you're going to sit down and practice an essay question for. Just a little bit about what each of these types of white blood cells do collectively to help protect us against infectious disease. You might want to be aware of those for next Thursday's exam. What I'd like to talk a little bit more about in a little more detail, your book spends a little more time on this. Here we're looking at not cells that are found in our blood, but fragments of cells. If we take a look at this micrograph, we have these little purple staining chunks. Note that they are smaller than these red blood cells. These are fragments of cells. These are called platelets. Sometimes they're called thrombocytes. I'll call them platelets to be consistent with your textbook. These are fragments of cells that can, under some circumstances, attach to surfaces. So they can be sticky, they can adhere or attach to different surfaces in the body. And they also contain actin and myosin. What does that mean? We like actin and myosin here. What do we know about actin and myosin here? They're able to contract. So we have actin and myosin in these cellular fragments. They're able to contract a little bit with our sliding filament theory. We'll see how that is important here in a little bit. These don't exist for very long. They exist in our body for about a week. So our cells are constantly, our stem cells in our bone marrow are constantly producing more of these platelets. They're only around, an individual platelet only exists for somewhere on the order of a week. And their main function is what we call hemostasis, or the control of blood loss. Don't confuse hemostasis with homeostasis, right? Homeostasis, we're just talking generally about maintaining constant internal conditions. Hemostasis, hemo refers to the blood. We're trying to maintain a relatively constant blood volume. So that's what hemostasis is. We're trying to maintain our blood volume at a relatively constant level. And one way to do that is to protect against loss of blood. If there's damage to our tissue, we want to make sure we're not losing excess blood. That would throw off hemostasis. So here we're looking at the role of platelets in hemostasis. So first off, when you look at this figure, these kind of look like erythrocytes. I might have drawn these a little bit differently. These represent platelets that are in their inactive form, as they would be floating around in the blood. So we've got these little tiny cell fragments floating around in our blood. Those platelets, under normal conditions, when there is no damage to the blood vessel, those platelets are in inactive form and they're not sticking to surfaces. If we look at what keeps these platelets in an inactive form, we have several things that are keeping the platelets inactive. First off, we have PGI2. This is an abbreviation for a type of prostaglandin called prostacyclin. Prostacyclin is inhibiting platelet activation. If platelets become activated, they are going to become sticky, they're going to adhere to tissues, they're going to kind of plug up wounds. So prostacyclin is keeping those platelets from being activated under most conditions. NO, in which, if you've been kind of following along in your textbook, it gets mentioned here and there. This is nitric oxide. It's a signaling molecule. Nitric oxide is also produced in our blood vessels. Nitric oxide also inhibits platelet activation. So here we see prostacyclin, here we see nitric oxide. They are inhibiting activation of platelets. ADP, we've talked about ATP this semester. We've also talked about ADP. This is our lower energy form of ATP with 2 phosphates. ADP is involved in activation of platelets. If platelets sense high concentrations of ADP, those platelets become sticky, they're activated, now they're able to stick to surfaces in the body. ADP is typically not present in high concentrations in our blood plasma because of another molecule. You see it here, they look like these little pills. This is an enzyme called CD39. CD39 is present on endothelial cells. Endothelial cells, you know what that means? Ever heard that? Epithelial cells are our skin. So this is a cell that's lining inside of our body. Specifically, when you hear about endothelial cells are lining blood vessels. So CD39 is present on those endothelial cells that are lining blood vessels. What CD39 does converts adenosine diphosphate to adenosine monophosphate plus an inorganic phosphate. Essentially, that's what you're seeing up here. CD39 is taking this ADP, which can activate platelets. It's removing the phosphate, converting it into AMP, which has no effect on the activation of platelets. So in this situation, we have our platelets inactivated, and they are happily flowing along the individual other hand, we were to have damage to the tissue, and here we have damage, it's kind of shown as the removal of an endothelial cell. You can think of that as a kind of crude way of representing vascular damage. Now we see our platelets become activated. First off, on the previous slide, there's VWF. This is von Willebrand's factor. This allows platelets to adhere to tissue. When we see damage to a blood vessel, we now have exposed von Willebrand's factor, like you see here in this next image. Von Willebrand's factor is exposed. This is promoting the adherence and activation of platelets so they can stick to the underlying tissue. Also, at this point, we have new signaling molecules that are produced by damaged tissue. We have thromboxane A2. Produced by damaged tissue. That thromboxane A2 that is being produced by damaged tissue serves to activate platelets. So what we are now seeing is activation of platelets, their ability to adhere or physically attach to tissues has been stimulated. Their binding to collagen and von Willebrand's factor in this damaged tissue. We are starting to form what we call a platelet plug. And the idea is to take this damage in that blood vessel and then start plugging it up. Platelets are playing this major role in starting to stick here and kind of put a cork in the hole of the dam, if you will. Kind of stop that blood from leaking out of the damaged blood vessel. Accompanying this is something we call a vascular spasm, where we see the blood vessels decrease in diameter. They constrict a little bit, and this involves smooth muscle. This kind of gives us a little bit of preview of our next chapter. What happens to the amount of blood flow into a tissue when we take blood vessels and we constrict them? What effect is that going to have on blood flow? It's going to decrease blood flow. So this vascular spasm is decreasing blood flow. This happens in response to damage to the blood vessel. Why would this be? Does this make sense? You're trying to reduce locally, you're reducing the flow of blood along that damaged vessel. This is the body's way of helping to reduce the loss of blood in the environment until that damage can be patched and repaired. Until we can form a clot or a platelet flow to repair that. So this vascular spasm is reducing our blood flow. We have activation of platelets, helping to plug up this damage. Ultimately, we may have some activation of fibrin, which is found in the blood plasma, and we start to form a clot here. Now, if we have very, very small abrasions in our blood vessels, this is typically sufficient. This is typically sufficient to plug up and stop the bleeding. Very minor damage. If we have major damage, on the other hand, we see actual formation of a clot. And when clots form, there are a lot of other proteins. It's a lot more complicated than this. So I don't want to get into that level of discussion like you see in your textbook. I want to kind of gloss over this process of blood clotting. Here we're looking at an electron micrograph of a blood clot, and what you will see is this massive network of fiber proteins This has trapped red blood cells. We're forming kind of a mesh-like net that is trapping red blood cells along with those sticky platelets. Here we're really trying to patch major damage to blood vessels. We're forming a clot to staunch the loss of blood to the environment. So again, if we think about formation of a platelet plug like we saw up here, this doesn't work. This isn't enough to repair a relatively large cut in a blood vessel. We need clotting in order to deal with larger wounds. Thinking very generally about the clotting process. Again, I don't want us to get into the details. There's a lot of proteins involved in the clotting process. And I don't want to get involved in those details. The big idea, we have a lot of proteins that circulate in our blood in an inactive form. Those proteins that are involved in causing clotting tend to be activated by damage to blood vessels. And so we see cascades where multiple proteins get activated when they're in the region of a damaged blood vessel. I don't want to go through all the individual proteins. I think it's a little bit beyond the scope of what we're trying to do here. But keep in mind that clotting can be stimulated by chemicals from outside of the blood. So we may have tissues that are surrounding our blood that are secreting signaling molecules, or we may have tissues inside, cells from inside of the blood, secreting signals that are causing the clotting reaction to occur. We have basically two pathways that cause blood clotting. We have the extrinsic and the intrinsic pathway. Big idea, they're going to both work together to cause the production of clot. Again, I don't want to get into too much detail of blood clotting, because if you look at this figure, it is pretty complicated. I think one physiological thing to keep in mind is that there are individuals who have disorders where their blood does not clot properly. Does anybody know of a disorder in blood clotting that is inherited? It's genetic. And it is found primarily, not exclusively, but it's found primarily in males. These individuals often require transfusions of blood that has the appropriate clotting factors. These individuals are defective in at least one of these clotting factors, and their blood has a very difficult time clotting. If they were to cut themselves, they bleed very readily. If they were to bruise themselves, they tend to bleed internally very profusely. They bruise really bad. This disease used to be a major risk factor for contracting HIV before blood samples were screened in the United States, starting at, I think it was 1985. Many individuals, including children, contracted HIV by getting blood transfusions because they have this disease. What letter does it start with? Can anybody get a guess? H. Absolutely starts with an H. Hem something. Hemo something. There we go. Hemo. Hemophilia. Very good. Hemophilia. So if we think about hemophilia, many individuals with hemophilia, they have defects in one or more of these proteins. The genes for these proteins, many of them are found on the X chromosome. Guys only get one copy of an X chromosome, so we only have one chance to inherit the genes for these proteins. If we have a defective gene on our X chromosome, males don't have a backup. Females can get hemophilia. They have to have two X chromosomes with defective genes. So we can see this in females. But this, like many traits, like pattern baldness, for example, color blindness, is a trait that is far more common in males than females because the gene that controls this trait is found in the X chromosome, and males only get one. Not something I'll have time to expand on, but certainly there are disorders that are more common in males. If they are genetic disorders, it's because those genes are found in the X chromosome. Taking a look at our pathways for clotting, we have the extrinsic factor, where we have surrounding tissues that are secreting molecules causing clotting. Here we have the intrinsic pathway, where things like collagen or glass that may find themselves in the blood may come in direct contact with collagen if the tissue has been damaged. These are going to stimulate the intrinsic pathway. The only part of clotting that I want to hold you responsible for are two proteins. These are the last two. They're part of the common pathway that both the extrinsic and intrinsic pathway activate. Prothrombin is converted to thrombin. So prothrombin, when you see pro preceding the name of a protein, typically that means the protein is in an inactive form. So prothrombin, looking at our clotting pathway, prothrombin gets converted to thrombin when we are activating our intrinsic or extrinsic pathways. Thrombin then catalyzes the conversion of fibrinogen. Again, prothrombin is inactive. Thrombin is active. Fibrinogen is inactive. Thrombin catalyzes the conversion of fibrinogen into active fibrin proteins. When fibrinogen is inactive, we see it soluble. It's kind of suspended there in the plasma. When it's activated, we see fibrin. We see it coming out of solution, and we can see right here, we can see our network of fibrin proteins appearing. So these are coming from fibrinogens that are inactive at all times in our plasma until the clotting pathway is activated. We then see fibrinogen polymerize to form fibrins. Now we see our clot beginning to form. So we're making use of proteins that are always there in our plasma in an inactive form when we activate this clotting pathway, either by secreting tissue factors from other tissues or by exposing the blood to collagen or to glass. We then activate these proteins. We'll get the production of fibrin and clot formation. So a key thing to keep in mind is the more thrombin you have activated, the more fibrin gets activated. This actually is going to form positive feedback, where we get more and more activated fibrin showing up. So, where did I go there? There we go. This is positive feedback, and our clot formation is going to accelerate. So our body has to have a way to put the brakes on this reaction. This is an important thing to keep in mind. When our blood starts to clot, if we can't put the brakes on that clotting reaction, it's just going to run out of control, and we're going to start seeing all of our blood clot. That's a terrible thing. So our bodies produce, to help slow down the clotting process, we produce anticoagulants, we produce antithrombin, heparin. Has anybody heard of heparin medically? Why would we give a patient heparin?
It's a blood.
Is it what?
It's a blood thinner.
Why would we give them a blood thinner? Oh my gosh.
Like,
Why would we do that?
they have blood clot in their lung.
Absolutely. Maybe they have a pulmonary embolism. With a patient with a pulmonary embolism, they have a clot of blood that is lodged in their lungs. Am I right? This is extremely painful for the patient. This is terribly discomfortable, and it can lead to death. We give them a blood thinner with the idea of trying to reverse this clotting process to get rid of and dissolve this clot. So we don't have an embolism in the lungs. Stroke, heart attack, we might give heparin to help dissolve whatever may be blocking arteries in the brain or in the heart. So these are blood thinners that can be given. We naturally produce them. They can also be administered to patients to help decrease clotting. Let's see. As we get away from the site of damage, the clotting factors get diluted out very, very quickly. They get inactivated. So typically clotting is a very localized occurrence. We have to have those signals present in a localized area to get a high enough concentration to activate the clotting factors to actually see clotting occur. But it's really important, again, when we have patients where we see inappropriate clotting. This is a real concern. In elderly patients, we may see a thrombus develop, an inappropriate clot. That could happen maybe somewhere in the leg. Let's say we have a patient that starts to develop an inappropriate clot in the venules of their leg. If a piece of that clot were to break off and enter circulation here in the leg, remember it's in the venules, so it's starting to head out of the capillary beds. If a piece of an inappropriate clot, thrombus, were to become an embolism, break off, and spread back into circulation, what is the next capillary bed that clot is going to find itself in? There's an venule in the leg, it's going into the veins. Where's the next capillaries it finds itself in? It's going to make its way back to the heart. When it goes into the heart, does it immediately go into capillary beds? When the blood is coming back, this is preview. This is a preview of what should be a review. It's coming up later on in this chapter. I'm previewing a review we're going to do later on in the chapter. When blood is coming back from our bodies, such as our legs, back to the heart, what is the first chamber of the heart that blood goes into? It goes into the right atrium. No capillaries in the right atrium. From the right atrium, where does the blood go? Down into the right ventricle. Thick, heavily muscled chamber of the heart. No capillaries. When the heart contracts and it forces blood out of the right ventricle, where does that blood then go off to? It goes off through the pulmonary arteries, which lead to the lungs. So what are the first capillaries that clot's going to find itself in the lungs? So when we see patients, this is why it's such a severe concern. It can be a problem if patients are developing blood clots in their legs. It can be a problem for blood circulation in the legs, certainly. But a huge concern with that is that pieces of those clots break off and become mobile in the body. The very next capillary bed they're going to find themselves in is in the lungs. These patients are at high risk for the development of pulmonary embolism, where we have blockages of circulation in the lungs coming from inappropriate clotting elsewhere in the body. So often if we see patients that are showing inappropriate clotting in the legs, we will give them blood thinners, hopefully to prevent any clots from breaking off and then lodging in the lungs. If somehow that clot doesn't lodge in the lungs, it makes its way through and it goes back into the heart, it goes back into systemic circulation. We're talking to the left side of the heart. Those clots can be sent elsewhere in the body. They can find themselves in the brain. What happens when we have a blood clot in the brain? What do we call that? It causes a stroke. We could have a blood clot lodging in the arterioles or capillary beds of the heart. What would that cause? It causes a heart attack. So this is a common reason why we would give blood thinners. Aspirin is going to act as a cyclooxygenase inhibitor. It's going to cause blood thinning by acting on prostaglandins, like we talked about at the very end of chapter 11. We try to thin out blood, reduce that inappropriate clotting to prevent any clots that may be forming privately elsewhere in the body, causing embolisms. So just a little bit about blood clotting in a normal situation where we want that clot to form, where there really has been damage. We see, once the clot forms, it begins to condense in clot retraction. It kind of starts to shrink up. Part of that is involved, especially if we are looking at a clot that is formed on the outside of the body. Part of that is due to the evaporation of plasma. We kind of dry up and we help shrink that clot a little bit. We're forming what we typically call a scab. But there's also actin and myosin in our platelets, and like I mentioned earlier, that causes our platelets to contract. The platelets contract and they help pull that damaged tissue back together. They help to retract that clot, help to shrink it up. It helps to pull the damaged tissue back together to promote healing. The fibrin doesn't stick around forever because we have another enzyme called plasmin. Plasmin is going to degrade fibrin. And eventually our clot is going to dissolve once that tissue has been. This is something that some pathogens, some organisms that cause disease. There are some organisms that can cause inappropriate clot formation. They can cause fibrin or thrombin to become activated. You can see organisms that are causing, maybe they're causing a boil in the skin. They can promote the activation of thrombin. They form a clot surrounding that site of infection. It makes it really hard for our white blood cells to be there and fight off that infection. Other organisms, they have the ability to spread from the site of infection by activating plasmin. Those organisms can move from being a localized infection by dissolving clots that your body might have formed. They can spread out systemically in the blood, and they can potentially cause a system clot or infection. So looking at how this process normally works in the body leads us to a little bit of insight into how infectious microorganisms can manipulate this and isolate themselves from white blood cells or cause themselves to spread in the body. And if you start reading about some toxins that some microbes produce, those are just a couple of examples. Those of you in micro, you will actually see this. I think it's our exercise 13 lab. How many of you were in micro? A few of you were in micro. That one is, I'm going to think about for exercise 13, which is their answer out here. Okay. Anyway, just a little bit about blood clotting. That's all I wanted to say about the blood for now. We'll come back to blood's ability, especially hemoglobin's ability, to bind oxygen and deliver it to tissues. That's going to show up when we talk about respiration. So we know that hemoglobin is involved in oxygen transport. We haven't really talked about the physiology yet of oxygen transport. Your book covers that in our chapter on respiration. So we'll specifically come back and discuss hemoglobin in a bit. Does anybody have any questions? Let's move on and talk about the heart. We have done human blood typing. I'm not going to talk about that any further. We've seen all that in the lab. I know you'll be familiar with that for our upcoming exam a week from today. Today, right? Today's Thursday. All right. Let's focus in on the heart. This is where we're going to get to in our lab today. We're going to start looking at some features of the heart, and I'm going to make you work, not just mentally, but physically. We're going to do some exercise, some of you, in lab today. So think about if you want to do some exercise. We'll take a look at the effects of exercise on your heart. Big functions of the heart, thinking globally about our heart. What does it do? Well, first off, it is going to generate blood pressure. We're not going to get into a discussion of blood pressure here. Our next chapter is related. We're looking at cardiovascular physiology. Chapter 14 will consider blood pressure. about blood pressure, the heart is contracting, it is generating a force, it's compressing the blood and putting a force on that blood. That force is propelling our blood through our arteries. So it's helping our blood move in one direction through our blood vessels. As you all have seen in your anatomy class, the heart is involved in routing blood. I would encourage you to visualize the heart as essentially two pumps that are attached together. Think of the heart as two separate pumps. One of the pumps deals with blood that is low in oxygen, and it sends that blood to our lungs. The other pump that is physically attached, the other pump, deals with blood that is high in oxygen, and is sending that blood off to our body. And so we see the heart involved in routing blood to certain locations in the body. This is how it works in mammals. It's not how it works in all animals. If you do some comparative physiology, you find that mammals, that's you and me, we have 4-chambered hearts. We'll see other organisms that have 3-chambered hearts, or even 2-chambered hearts. A mammal is not 4 chambers. So we have the most complex heart of all the animals. The heart ensures one directional blood flow if we're talking about a normal, healthy individual. We have valves in the heart, as well as in our veins. That keeps the blood from flowing backwards. So as we follow the flow of blood through the heart, we will see that blood in a normal, healthy individual is only flowing in one direction. We don't see the direction reverse in the heart. And a big topic in our next chapter, we will see, we'll touch on this in lab today, we'll see how the heart regulates blood supply. Our heart can dramatically increase the amount of blood that is pumping in any given unit of time based on contracting more frequently and more forcefully. We think about a normal heart rate right now, my heart is probably pumping somewhere on the order of 4.5 to 5 liters of blood per minute. That can increase dramatically depending on how well trained an athlete is. We may see that go to 20, maybe 25 liters per minute as the heart rate increases and the force of the contraction increases. So we'll talk in our next chapter about how the heart regulates blood supply by changing the rate of contraction and by changing the force of contraction. So you see where we're going. Just to review very quickly what we have learned in anatomy. We talk about systemic and we talk about pulmonary circulation. In this figure, we have low oxygenated blood shown in blue, high oxygenated blood shown in red. If we focus in on the heart, let's take a look starting right here. This is the right atrium of the heart. You will notice that we are receiving poorly oxygenated blood from these tissues. Right here, these tissues, this represents just the rest of the body, pretty much everything but the lungs. We're talking about poorly oxygenated blood coming back from the upper regions of the body, coming back from the lower regions of the body. These tissue cells are not meant to indicate any particular anatomical structure. It's just all of the tissues that are around our body. We see, coming back to our heart, you've learned about the superior and inferior vena cava. Superior vena cava bringing blood back from our upper extremities. Inferior vena cava bringing blood back to the heart from the lower extremities. That poorly oxygenated blood makes its way to the right atrium. When we look at how the heart contracts, we will see that the atria contract before the ventricles. So the atrium contracts. It forces blood down here into the ventricle. Notice how much thicker the wall of the ventricle is. We're going to put a lot more force on the blood when it's in the ventricle. When the ventricle contracts, this forces blood out the pulmonary arteries, which are shown in blue. The pulmonary arteries lead off to the lungs. into the left atrium, just like we see on the right side, when the heart contracts, the atria contract first. They force blood down into the ventricles, then the ventricles contract. Blood moves from the left ventricle out into the aorta and off to the other tissues of the body where oxygen can be delivered to tissues. And then we continue the cycle. So think about the right side of the heart. It's dealing with poorly oxygenated blood from the body, sending it off to the lungs. The right side of the heart is dealing with pulmonary circulation. The left side of the heart is receiving well-oxygenated blood from the lungs, sending that well-oxygenated blood off to the body. The left side of our heart deals with systemic circulation. That should be reviewed. Does that sound familiar? We heard this in our anatomy class. This should be reviewed. I don't know if I spent too much time on it. Are you hearing anything shocking here or what? I've heard this before. All right, good. So I want to focus more on the physiology. Keep in mind, looking at the anatomy of our heart, this is not an anatomy class, but I want you to bear in mind the importance of the valves. We have the semilunar and the atrioventricular valves. Where do we find, doesn't hurt to do a little bit of review here, where do we find the semilunar valves? I'm sorry? Those semilunar valves. For example, we see one of the semilunar valves that is separating the pulmonary trunk from what? What part of the heart? You've gotten through three. It's not the right or left atrium, it's not the left ventricle, it's the right ventricle. The semilunar valves, one of them separates the pulmonary trunk from the right ventricle. Another one separates the aorta from the left ventricle. If we take a look at the anatomy of the heart, it's okay if you didn't remember this right off the bat. This should be reviewed. I don't expect it to be right there on the tip of your mind. But if we take a look at our pulmonary valves, here we have, if we look at our semilunar valves, here we have the pulmonary semilunar valve. It is separating the right atrium, right ventricle. All of this is the right ventricle. It is being separated from the pulmonary trunk, which branches into the pulmonary arteries. We see, where is it at? Are you going to show it to me here in this figure? You're not going to show it to me in this figure. If you were to go back here, behind the aorta, and follow it down here into the left ventricle, there is another valve right back here. You can't see it because our right ventricle is in the way. Right here we have the aortic semilunar valve. So the semilunar valves are separating the ventricles from the blood vessels. We also have the AV valves, atrioventricular valves. These are exactly what their name implies. These are found between the atria and the ventricles. We have our tricuspid. The tricuspid valve, this is between the right atrium and ventricle. We have the bicuspid, sometimes called the mitral valve. This is between the left atrium and ventricle. These valves are going to be absolutely critical in the generation of blood pressure as well as the regulation of blood. What I'd like to do is take a look at the cardiac cycle. We'll take a look at how the blood moves through the heart when the heart is beating. How are we doing? Holy crap, it's almost 2 o'clock. Must have fallen asleep there for a bit, I'm sorry. I realize it's 55 minutes. Have you ever had that happen where you just like doze off? I was drinking coffee this morning. I do that every morning. I was drinking coffee this morning. It was like 4:15. And I'm like, I'm drinking my coffee. 5 o'clock. Boom, like that. What the hell happened? All of a sudden it's 5. I time traveled this morning. 45 minutes. Boom. I think in reality I actually fell asleep. But it felt like I just was on the head 45 minutes. I just had that same feeling again right now looking at the clock. I can't believe it's been 55 minutes. By the looks on your faces, I now do believe it has been 55 minutes. Because y'all look like you're flagging a little bit. Let's talk about the valves. Pretty quick here, I'll give you a break. Okay? Any questions right now? Take a look at our valve positions. Our valves can open and they can close during the heartbeat. What we've got here is a situation where our atrium is contracting. And what can happen as the atrium begins to contract, we have an open, we're looking on the left side of the heart here. So our bicuspid valve is open. Note that our aortic semilunar valve is closed. What we're doing is we are filling up the ventricle. You can see the ventricle kind of swelling and expanding. So one valve is open, we have blood flowing into the ventricle from the atrium. The other valve that is controlling the passage of blood out of the aorta is closed. When our heart goes into contraction, when our ventricles contract, it's not shown right here, for a brief second, just a real quick second, all of the valves are closed and the heart is contracting. What happens in the brief moment when both valves are closed and the heart is still contracting? What happens to the pressure of the blood in the ventricle? It builds. Think about what would happen if you take a water balloon and you squeeze it. You're building up pressure in the water inside of that balloon. What's going to happen when the pressure gets too high? Balloon's going to burst. Our heart does not generally burst. This is not something that happens. We are squeezing the blood in our ventricle. We're driving the pressure of the blood up in the ventricle. Instead of our heart just going to blowing up, which would generally not be a good thing, it causes a force on our aortic semilunar valve. It forces that valve to come open. We have blood that is at high pressure being forced out into the aorta. So think about the valves as helping to generate blood pressure. We have a brief moment every time our heart contracts. When all of the valves are closed, whatever blood is in the ventricle is momentarily trapped there while the ventricle is contracting. And that generates a large amount of pressure or force in that blood. That pressure then forces our semilunar valve open. We have blood leaving the heart at high pressure. And that blood pressure, at that high pressure, is going to be very important, helping to ensure that the blood is flowing in one direction around our body. It's going to be very important, helping to manage fluid exchange with the different tissues of the body. These are things we'll talk about in chapter 14. So when you're listening to somebody's heart, we're not going to do this in lab, but when you are listening to somebody's heart, you hear the sound. That sound you're hearing when you listen to a heartbeat, it is not the muscle contracting and relaxing. That's a common misconception. People think, oh, I'm hearing the heart, that's the muscle contracting and relaxing. That's not the case. It doesn't make sound. The contraction doesn't make sound any more than, moving your leg would make sound. The that you hear from a heartbeat, this is the opening and closing of valves. This is blood that's hitting the valves and flowing back and causing turbulence. that is giving you an audible sound. So it's the opening and closing of valves that's causing those audible sounds. When you listen, or you have a doctor listen to your heart, they are listening for an abnormal sound, which we refer to as a heart murmur. When you have a heart murmur, you have a valve that is either incompetent, that valve doesn't close sufficiently, and we get a backflow of blood, it's going backwards from the way it should go. That's going to cause some strange sounds, because we now have blood flowing back into the atrium, for example. Or we have congenital defects, birth defects, where the valves are stenosed, where they have abnormally small openings, and we are restricting the flow of blood across those valves. That will also cause a murmur. It also causes an abnormal heart sound. So this is why they listen to your heart. They're making sure that valves are opening and closing properly. We're making sure we have an efficient flow of blood through the heart. This is a wonderful time for us to take a 5-minute break. We'll talk about the cardiac cycle when we come back. Go ahead and take 5 minutes, come back about 2:05, and I'll see where we are.